Hello, this is the third video of the fifth calculus series for OCR Pure Core Further Mathematics, and it looks at the volume of revolution of a solid created by rotating a curve f of x around the y-axis. You may like to imagine a potter throwing a pot on a rotating wheel. Here we have the region between the curve y equals f of x, the y-axis, the lines y equals c and y equals d, being rotated 360 degrees around the y-axis to give the solid shown. We are still going to get a collection of cylindrical discs that will need to be summed to give the volume. However, these will be stacked vertically rather than horizontally as in the previous video when we rotated around the x-axis. In this instance, you can see that the height of the cylindrical discs will be delta y, and that the radius of the discs will be the x value. Therefore, the small volumes of the cylindrical discs will still be the cross-sectional area times the height. But in this case that will then be pi x squared, x being the radius, times the height delta y. And in the limit as delta y tends to 0, the total volume will be the integration with respect to y of pi x squared between y equals c and d. It's important to notice the integration is carried out with respect to y rather than x, and the limits of integration are the y coordinates rather than the x coordinates. It will also be important to express the x squared as a function of y in order to integrate with respect to y. In this example here, we have that y equals 2x to the 0.5. If we square both sides, we would have that y squared equals 4x. So we can write x equals y squared over 4 as our function of y. When we come to integrate, the limits c and d will be the y values 2 and 4, as shown in the diagram, the text above. We will multiply by pi, and then the x squared will be this y squared over 4, remembering to square it, that's important, and integrating with respect to dy. This will give us, and here I'm going to take out the pi and the 16, an integral of y to the power 4, which integrates to y to the 5 over 5. Again, those limits 2 and 4. So I might choose to take out the 5 as well. But using my calculator, I would find that that is 62 over 5 pi. And it will be whatever the units are cubed because it's a volume. This example may show or highlight some of the common errors that are made. Here we have a region bounded by the curve y equals x squared minus 3. The y-axis, the lines y equals 4 and y equals 5, rotated 360 degrees around the y-axis, and we need to choose the correct calculation to find the volume of revolution. For ease, we've put the formula in a box on the same slide. Looking first, we can see that we've integrated, so that's correct. We can see that we've chosen the lines y equals 4 and y equals 5 as the limits for all of them, so all of that is correct. We can see that in terms of getting a pi, the second choice does not have a pi in it. so forgetting the pi is a problem. And let's also look at the y plus 3. If we have y equals x squared minus 3, then we can rearrange that to being x squared equal to y plus 3. So that part was correct, but there we were missing the pi. Looking therefore at the top choice, what they've actually put in there is y rather than x squared. So making sure we actually use x squared is important, unless of course you're integrating a volume of revolution about the x-axis. Looking at the third one down, we've got y plus 3, which is indeed x squared, but we've integrated with respect to x. So that is wrong. You must integrate with respect to y. Finally, in the last one, we have got the right limits, the integration, the pi, the x squared, and integrating with respect to dy. So that is correct. In the next video, we'll be looking at volumes of revolution where the curves are defined parametrically.